We'll start in 1 minute. We'll continue with the final exam review. We'll finish part 1 and then start part 2 after that. The final exam is cumulative over all of the material that was covered, and we'll have the final on Wednesday, December 2nd from 7:30 a.m. to 9:30 a.m. Mountain Standard Time. Okay, last time we were working on trig substitutions. I went ahead and finished this one and wrote it more compactly. We didn't get all the way to the end on Friday. But for this one, the integral of the square root of a squared minus x squared dx, we chose x equals a times sine of theta. And so dx is a times cosine of theta d theta. And the a to the second minus x squared with that substitution simplifies to a squared times cosine of theta squared. That's the expression that goes inside the square root. And so the integrand becomes a to the second times the integral of cosine of theta squared d theta. And then we use the identity for cosine of theta squared, which is 1/2 times the quantity 1 plus cosine of 2 theta. And then computing the integral, the constant a to the second divided by 2 is multiplied by theta plus 1/2 sine of 2 theta plus a constant. And then we use the identity for sine of 2 theta, which is the identity we used is 2 times sine of theta times cosine of theta. So when you multiply that by 1/2, you just get sine of theta times cosine of theta. And all that's left to do after this is replace sine of theta and cosine of theta. X equals a times sine of theta, so we'll replace sine of theta with x over a and replace theta with the inverse sine of x over a. And then in terms of x, we can easily find that cosine of theta is the square root of a squared minus x squared over a. And then we make that substitution, and we get this formula for the square root of a squared minus x squared. Okay, let's do the next one. So I'll just mention, you won't be deriving formulas on the final exam, but you might have to use one of these trig substitutions. So that's why we're practicing the trig substitutions, not simply deriving formulas. So on this one, the integral of dx over the square root of x squared minus a squared. For the x squared minus a squared, the trig substitution we'll use for this one is x equals a times secant of theta. And so dx is a times secant of theta tangent of theta d theta. and then x squared minus a squared. That becomes a squared times secant of theta squared minus a squared. Factor a squared out of both terms, a squared times secant of theta squared minus 1. But secant of theta squared minus 1 is tangent of theta squared. So this is what we'll put inside the square root in the denominator. And we'll replace dx with a times secant of theta tangent of theta d theta. And I'll do two steps in one. We're going to have the square root of a to the second times tangent of theta squared, and that will simplify to a times tangent of theta after we take the square root. And then we can simplify this integrand. A divided by a is 1, and tangent of theta divided by tangent of theta is 1. So we get the indefinite integral of secant of theta d theta. And the antiderivative for secant of theta is the natural log of the absolute value of secant of theta plus tangent of theta, and then plus a constant. And we want to replace secant of theta and tangent of theta with expressions in terms of x. Our assignment, x equals a times secant of theta, we can see that secant of theta is x divided by a. And if we use right triangle trigonometry, we can come up with an expression for tangent of theta. So if we construct a right triangle, this is angle theta. If secant of theta is x over a, then the hypotenuse is x, the adjacent side is a, and the opposite side of theta is the square root of x squared minus a squared. And so tangent of theta is the square root of x squared minus a squared over a, opposite over adjacent. Okay, so our integral then becomes the natural log of, instead of secant of theta, we write x over a. And instead of tangent of theta, we write the square root of x squared minus a squared over a plus a constant. Since we have a common denominator that is a constant, a, and using properties of logarithms, we can write this as the natural log of the absolute value of x plus the square root of x squared minus a squared minus the natural log of a plus a constant. But since minus the natural log of a is itself a constant, you can just replace minus the natural log of a plus c with another letter different than c, maybe k or something. Okay, so that's what we get using that trig substitution. Yeah, on the next page, integration of rational functions by partial fractions. So for this first one, we'll find the form of the partial fraction expansion, but we won't bother finding the constants. Okay, so the denominator is x squared plus 9 quantity squared times 4x minus 1 quantity to the fourth. You'll recognize x squared plus 9 as an irreducible quadratic expression, meaning that it cannot be factored over the real numbers. So I'll probably run out of room up there. So down here, for one factor of x squared plus 9, the numerator will have the form ax plus b. And this is over x squared plus 9 to the first. But then we need another one, cx plus d over x squared plus 9 squared. Okay, so that takes care of the irreducible quadratic to the second power in the denominator. And what about the rest? The rest of this partial fraction expansion? Well, what we have left in the denominator is a linear expression raised to the fourth power. 4x minus 1 is linear. So for the numerators will just be constants. So we're up to the letter e, the constant e over 4x minus 1 to the first, and then f over 4x minus 1 to the second, and then g over 4x minus 1 to the third, and then the final one, 8 over 4x minus 1 to the fourth. So that's all you had to do on that part. The next one, though, evaluate the indefinite integral of 5x over x squared plus 5x plus 6. So the denominator can be factored easily enough, x squared plus 5x plus 6. We get two linear factors, x plus 2 and x plus 3. So we'll use a partial fraction expansion, and then after that, we'll find the integral. So 5x over x plus 2 times x plus 3. The two factors in the denominator are linear, so we'll have a constant a over one of those factors, x plus 2, plus a constant b over the other linear factor, x plus 3. Okay, so writing this as a single rational expression, we get ax plus 3a plus bx plus 2b all over x plus 2 times x plus 3. So what does this imply? This numerator, ax plus 3a plus bx plus 2b, has to be equal to 5x. So in other words, a plus b, the quantity a plus b times x, plus 3a plus 2b has to add up to 5x. So we get a system of two linear equations in the variables a and b. A plus b is the coefficient of x, so a plus b is equal to 5. Plus 3a plus 2b, those have to add up to 0. So 3a plus 2b is 0. And we can easily solve this system of equations. So one thing we can do, we can multiply every term on both sides of this equation, a plus b equals 5, multiply both sides by -2. And we get -2a minus 2b equals -10. And then when we add those equations together, the b will be eliminated. 3a plus -2a is a. 0 plus -10 is -10. Okay, so the value of a is -10. And then to find b, we can use any one of those equations. We go ahead and use the top equation. Replace a with -10. -10 plus b equals 5. Then add 10 to both sides, we get b equals 15. Okay, so the integral then becomes the indefinite integral of -10 over x plus 2 plus 15 over x plus 3 dx. So what do we get when we find antiderivatives? Well, an antiderivative of -10 over x plus 2 is -10 times the natural log of x plus 2. And then an antiderivative of 15 over x plus 3 is 15 times the natural log of x plus 3. And then plus a constant. Okay, approximate integration. I might be wrong, but I believe that the trapezoidal rule and Simpson's rule are pretty popular as far as the way to approximate integration. So the trapezoidal rule, if you want to estimate the definite integral of f of x from a to b, the trapezoidal rule, t sub n is delta x over 2 multiplied by f of x sub 0 plus 2 times f of x sub 1 and so on. The last term is f of x sub n. So the thing to remember here when using the trapezoidal rule, n can be, for the trapezoidal rule, n can be odd or even. It doesn't matter if it's an odd number or an even number. And then outside of the parentheses is delta x divided by 2. With the exception of the first term and the last term, the other terms have a constant factor of 2. And then delta x is b minus a divided by n, as usual. For Simpson's rule, what you remember about the number n when we use Simpson's rule? Yeah, it has to be even. So remember that, n must be even if we're going to use the Simpson's rule to approximate a definite integral. And Simpson's rule gives you a better approximation than all of the other methods in general. So n must be even, so to approximate the definite integral of f of x from a to b, so s sub n is delta x divided by 3 multiplied by a quantity inside the brackets. So the first term inside the brackets, f of x sub 0, and the last term, f of x sub n, have a coefficient of 1. The other coefficients alternate from 4 to 2 to 4 to 2, and so on. So there's a missing right parenthesis. So this term is 2 times f of x sub n minus 2. And the delta x is found the same way, b minus a divided by n. Okay, the trapezoidal rule and Simpson's rule are pretty easy to memorize, but you are allowed 2 sides of a page of notes for the final. So if you can't remember it, make sure that you write that down. Hey, so for this example, let's use both the trapezoidal rule and Simpson's rule with n equals 4 to estimate the definite integral of x to the 4th dx from 0 to 8. So I suppose what I would do is first identify what delta x is. So the interval from 0 to 8, and we want n to be equals 4. So delta x is 8 minus 0 divided by 4, which is 2. So the length of each subinterval is 2, starting at 0. And then I'll just create a table of values over those intervals, subintervals. The subintervals are of length 2, but we start at x equals 0, and then 2, 4, 6, and 8. And then write down the function values. So when x is 0, 0 to the 4th is 0. When x is 2, 2 to the 4th is 16. When x is 4, 4 to the 4th is the same as 2 to the 8th, which is 256. When x is 6, 6 to the 4th, 6 times 1 is 36, times 6 is 216. 216 times 6 is 1296. When x is 8, 8 to the 4th, that's the same as 2 to the 3rd to the 4th, or 2 to the 12th. We know that 2 to the 10th is 1024, so 2 to the 11th is 2048. 2 to the 12th is 4096. Okay, then trapezoidal rule. T sub 4. So delta x over 2, 2 over 2. And then the first term is 0, and then plus 2 times 16 plus 2 times 256 plus 2 times 1296, and then plus 1 times 4096. So I'll let you add those up, and you can compare it with the actual number. For Simpson's rule, so out front we have delta x divided by 3. So delta x is 2 divided by 3. And then on the inside we have 1 times 0 is 0, and then plus 4 times 16 plus 2 times 256 plus 4 times 1296, and then plus 1 times 4096. So compare those two approximations with the actual exact answer. Okay, but we'll move on from here. Improper integrals. There's a comparison theorem for improper integrals. So we'll apply that here in a couple of problems. Use the comparison theorem to determine if the following improper integrals converge or diverge. So what do you think? Do you think this one converges or diverges? So what's our disadvantage?
That doesn't work guesses thing anyway.
Say what?
I don't know.
Oh, okay.
I think that is that one of those integrals that we don't actually know the solution to? So there are examples of those like that.
Well, if I think I know what you're saying, we don't have a function for an antiderivative of e to the negative x squared.
Right.
We do have a Taylor series, but this is before Taylor series was introduced. So we want to be able to determine if this converges or diverges by comparing it. So let's start out this way. The range of the x values are from 1 to infinity. So for x greater than or equal to 1, x squared is greater than or equal to x. Are we in agreement about that? And if you take the negative of both sides, negative x squared will be less than or equal to negative x. So what that should mean is that this improper integral of e to the negative x squared dx will be less than the improper integral of e to the negative x. So if we can determine, or if we can show that e to the negative x converges from 1 to infinity, that integral, then we'll also know that the original indefinite integral, not indefinite, improper, also converges. Okay, so we're going to compare this with the improper integral of e to the negative x dx. So the way we do it, we write this as a limit as b approaches infinity of the definite integral from 1 to b of e to the negative x dx. So we do know an antiderivative of e to the negative x.
Negative e to the negative x.
Yeah, negative e to the negative x. So this is the limit as b approaches infinity of negative e to the negative x from 1 to b. So the limit as b approaches infinity of the negative of e to the negative b minus the negative of e to the negative 1 So a little bit more arithmetic. So this is the negative of e to the negative b is negative 1 over e to the b. And the negative of the subtracting the negative is adding 1 over e. And then as b approaches infinity, the term negative 1 over e to the b goes to 0. And so the limit is a finite number, 1 over e. That means it converges. Okay, so since the improper integral of e to the negative x converges, the other improper integral, e to the negative x squared dx, also converges. But maybe I should have, I mentioned it, but I didn't write it down. So the key thing here is that the definite integral, or sorry, the improper integral of e to the negative x squared dx has to be less than or equal to the other improper integral of e to the negative x dx. So if this indefinite integral on the right converges to a finite number, the one on the left must also converge to a finite number. Okay, the next one, another improper integral. This one is 1 over the 4th root of x to the 4th minus 0.08 from 1 to infinity. So use the comparison theorem again. Compare it with,
1 over x.
yeah, that's what we're going to end up doing. So there's a clue here. We have 1 over the 4th root of x to the 4th minus 0.08. Well, the 4th root of x to the 4th is x, so we'll compare it with the improper integral of 1 over x from 1 to infinity. And what do we know about that improper integral?
It's the harmonic series and it diverges.
It diverges. Okay, but preliminary work. For x greater than or equal to 1, x to the 4th minus 0.08 is less than x to the 4th. We're in agreement? So the square root function is increasing for values of x that are positive. So the square root of the left-hand side, x to the 4th minus 0.08, not the square root, the 4th root, that's less than the 4th root of x to the 4th, which simplifies to x. And so the reciprocals will, the inequality will switch directions when we reciprocate. So this implies that 1 over the 4th root of x to the 4th minus 0.08 is greater than 1 over x. So this means then the improper integral of 1 over x from 1 to infinity has to be less than the other improper integral from 1 to infinity. But we know that this one diverges, the 1 over x from 1 to infinity. That improper integral diverges. Okay, does everyone remember how to show that diverges? Anybody not remember? It's not really too hard. I'll just do a couple of steps here. So just think of that as the limit as b approaches infinity of the definite integral from 1 to b of 1 over x dx. So this doesn't take too long. An antiderivative of 1 over x is the natural log of x. And then from 1 to b. Okay, so we get the natural log of b minus the natural log of 1. But the natural log of b, well, where does it go as b approaches infinity? Yeah, so this, we say informally this equals infinity, so in other words, it diverges. Do you know how to show that the limit of, do you know how to show that the limit of the natural log of b as b approaches infinity is infinity? It's one of those facts that we just assume that we know, but what if someone said, well, prove it?
Because every value is increasing, and so they don't go to a certain point.
Yeah, you can say if it doesn't go to infinity, it has to go to some finite number. And then if you can find a number that the natural log is bigger than that number. So I guess we won't do it now, but it's not really too hard. So let's move on then to the next page. Okay, so now we're starting on final exam review part 2. So the arc length formula. So the conditions, if f prime is continuous on the closed and bounded interval from a to b, the length of the curve y equals f of x for values of x from a to b is the definite integral of the square root of 1 plus f prime of x squared from a to b. And you can also use the Leibniz notation. Okay, so let's do an example. Find the length of the curve of f of x equals e to the x over 4 plus e to the negative x. Okay, so we need to find the first derivative. The derivative of e to the x over 4 with respect to x is e to the x over 4. And then the derivative of e to the negative x is negative e to the negative x. So we write minus e to the negative x. So I think what I prefer doing is rewriting this as e to the x over 4 minus 1 over e to the x. And then before squaring it, I'm going to write this as a single rational expression. So the common denominator is 4 times e to the x. And so in the numerator, I'll have e to the x times e to the x, or e to the 2x, and then minus 4. Okay, we have to square this and then add 1 to it and put that inside the square root. So let's go ahead and square f prime of x first. This won't be too hard. So when we square the numerator, e to the 2x minus 4, we're going to get e to the 4x minus 8 times e to the 2x plus 16. And the denominator is 16 times e to the 2x. And then when we add 1 to that, 1 plus the square of the first derivative. Well, with a common denominator of 16 e to the 2x, well, I'm skipping a step here. The common denominator is 16 times e to the 2x. So I'm going to multiply 1 by 16 e to the 2x. And we'll add it to this part, which is e to the 4x minus 8 e to the 2x plus 16. And then we have like terms that we can combine. So we're going to get e to the 4th plus 8 e to the 2x plus 16 over 16 e to the 2x. Okay, this is what's going to go inside the square root.
And question, would that be e to the 4th or e to the 4x in the numerator?
Which one?
Would that be e to the 4th or e to the 4x?
Oh, you're right. E to the 4x. Yeah.
Thanks, just making sure.
Yeah. I think we're okay now. Okay, this is the expression that's going to go inside the square root. And it turns out that both the numerator and denominator are perfect squares. So if we write this as e to the 2x plus 4 over 4e to the x quantity squared, this is the expression inside the square root. Okay, so when we take the square root of that, we'll just get the definite integral from 0 to 1 of the square root of that thing squared. So we'll just get e to the 2x plus 4 over 4e to the x dx. Okay, so let's simplify a little bit. E to the 2x over 4 times e to the x is just e to the x over 4. And then 4 over 4 times e to the x is plus 1 over e to the x, or plus e to the negative x. And then we can find antiderivatives. An antiderivative of e to the x over 4 is just e to the x over 4. An antiderivative of e to the negative x is minus e to the negative x. And then evaluate from 0 to 1. So when x is 1, e to the first over 4 minus e to the negative 1, which is minus 1 over e. And then when x is 0, e to the 0 is 1, so this is minus 1/4 minus 1. So kind of a goofy looking answer, but okay, let's move on to the next problem, area of a surface of revolution. Hey, on an interval where x goes from a to b, we let y equals f of x be greater than or equal to 0, or positive on that interval. And we also want it to be continuous and differentiable. And the surface area generated by rotating y equals f of x about the x-axis is given by this formula. It's the definite integral of 2 times pi times f of x times the square root of 1 plus f prime of x squared from a to b. This next one, or find the surface area generated by rotating f of x equals x to the third plus 1 over 12x for values of x between 1/2 and 1. The computations are pretty straightforward, but it is long and drawn out. So we'll just take it a few steps. We need to know what f prime of x is. So f prime of x is 3x to the second and minus 1 over 12x to the second. Okay, so if we write this with a common denominator, 12x to the second, then the numerator is 36x to the fourth minus 1. So we have to square that. So f prime of x squared so I'll just leave this as 36 squared x to the 8th minus 2 times 36 times x to the 4th, or minus 72 x to the 4th, and then plus 1 divided by 144 x to the 4th. And when we add 1 to that, the sort of thing that happened in the previous example is going to occur again. So 1 plus f prime of x squared. So if we convert 1 to 144x to the 4th over 144x to the 4th, and then simplify the numerator, this will become 36 squared x to the 8th plus 72x to the 4th plus 1 over 144x to the 4th. And both the numerator and denominator are perfect squares again. So we can write it as a single rational expression squared. So the square root of the numerator is just 36x to the 4th plus 1, and the denominator is 12x to the 2nd. Okay, so this is what's going to go inside the square root. So we can write down the surface area formula using the formula. So from x going from 1/2 to 1, 2 pi times f of x, which is x to the third plus 1 over 12x. And then we're multiplying that by the square root of this rational expression squared. So that's just the rational expression, 36x to the fourth plus 1 over 12x to the second dx. Okay, so we're about out of time. Like I said, the computations are pretty easy, just time consuming. But that's all we have time for today. So tomorrow we'll look at chapter 8 and chapter 9 material, and if time permits, chapter 10 material tomorrow.